Hello, this is the second entry in a series of discussion videos about curve sketching. So let us answer the second exercise problem. So it's asking us to graph analytically the following function. So f of x equals x minus 1 plus 4 over x minus 4. So first, if you want to graph a function, we should first check its domain. So the domain of f is simply the whole real numbers minus 4, because obviously this term is not defined when x is equal to 4. Okay? So 4 is not part of the domain of f. If we want to solve for that, we also would like to solve for the x and y intercepts of f. So if you want to solve for the x-intercept of f, you should just set f of x be equal to 0. So let us just solve for that equation over here. So if f is equal to 0, we have x minus 1 plus 4 over x minus 4. Okay. If we want to solve that, we have this equation is equivalent to, since x is never equal to 4, is equivalent to x minus 1 times x minus 4 plus 4. If we expand this product, we'll end up with some quadratic expression, and using the quadratic formula, we will end up with the following solution. So there is no real solution for this quadratic equation. Therefore, there should be no x-intercepts for f. So there should be no x-intercepts for f. If we want to find the y-intercept, we can just set x equal to 0 in this equation. So if we set x equal to 0 here, we'll find that the y-intercept is equal to, so this 0 minus 1 plus 4 over 0 minus 4. So that's negative 2. Okay. Next, let us find the asymptotes of f. We can readily solve for the oblique asymptote of f, since the limit of f of x minus x minus 1, so you just transpose these terms on the other side of the equation. So as x approaches positive or negative infinity, is equal to the limit of whatever remains on the right hand side, 4 over x minus 4, as x approaches positive or negative infinity, and this is obviously equal to 0. Therefore, this linear function is the oblique asymptote of f of x. Okay, so therefore y equals x minus 1 is an oblique asymptote for f. So let us take note of this. Next, to solve for the vertical asymptote, you just need to solve for the limit of f as x approaches 4 from the right or from the left. This is equal to 4 minus 1 plus 4 all over 4 from the right or from the left minus 4. This is equal to 3 plus 4 all over positive or negative, 4 over 0 from the right or from the left. So obviously, the limit of f of x as x approaches 4 from the right or from the left is equal to positive or negative infinity. So therefore, y equals 4 is a, sorry, not y equals 4, but x equals 4 is a vertical asymptote for f. And lastly, for the horizontal asymptote, note that the limit of f of x as x approaches positive or negative infinity is simply positive or negative infinity, because this term x minus 1 just blows up to positive or negative infinity, while this term becomes 0 as x approaches positive or negative infinity. And therefore, this is positive or negative infinity. Therefore, that means no such thing exists. Okay, so no horizontal asymptote for f. Okay, so we have two asymptotes, x equals 4 and y equals x minus 1. Now, let us compute for the critical numbers of f. To do that, we should first compute for the first derivative of f. I'm going to skip a lot of steps to save time, but you can use the quotient rule to find that the first derivative of f is equal to x minus 2 times x minus 6 all over x minus 4 squared. So this implies that the critical numbers are, well, just 2 and 6. 4 makes f prime of x non-existent. However, 4 is not part of the domain of f, so it shouldn't count as a critical number. Okay, so these are all your critical numbers, just 2 and 6. To solve for the possible points of inflection, we should compute for the second derivative, and I will just give the expression, the simplified expression for the second derivative. It's equal to negative 8 all over x minus 4 cubed. So this implies that The possible points of inflection are, actually there are none. Okay, this function has no zeros, and the only number that will make this undefined is 4. However, 4 is not part of the domain of f. Therefore, there are no possible points of inflection. Okay. Let us construct the table of signs for this function. Partition the real number line R using the critical numbers, the possible points of inflections, and the vertical asymptote. So the critical numbers are 2 and 6, and the vertical asymptote is given by x equals 4, so 4. Therefore, we will construct the table of signs like so. So we need the interval f, f prime, f double prime, and the conclusion. So in the interval negative infinity to positive 2, we have, and then for the next row, we have 2 to 4, 4, 4 to 6, 6, 4 to positive infinity. No, it should be 6 to positive infinity. Okay, for the first row, for this row, we'll see that f prime is positive when x is in the interval negative infinity to positive 2. So when x is less than 2, obviously this factor is negative, this factor is also negative, and this factor is always positive. So altogether, they imply that f prime of x should be positive in this interval. Okay, for f double prime, when x is less than 2, then x minus 4 is always negative. When you cube it, it's still negative. And then when you multiply it by negative 8, it comes out as negative. So we conclude that in this interval, f is increasing and it's concave downwards. It concaves downwards. So I'm going to fill up the rest of the table. Okay, I think these rows are quite self evident. Okay, but for these two rows, you can either use the second derivative test to make the following conclusions. So we know that when x is exactly equal to f prime is 0, so that means it's a critical number. And from the second derivative test, because f double prime of 2 is negative, then you can conclude that you have a relative maximum. Or you can just use the first derivative test. When x is less than 2, f prime is positive, and when x is greater than 2, f prime is negative. So by the first derivative test, okay, so by the first derivative test, 2 should be a relative maximum. You can make that a similar analysis for x equals 6. Oh no. When x is equal to 6, this should be negative. Should not be positive. Okay. Okay, so when x is equal to 6, you have a relative minimum. Okay, so let me make some corrections. I forgot to write out the conclusion for the row, for this row, for the third row. So when x is in the interval 2 to 4, we have that f is decreasing and it concaves downward. Also, when x is in the interval 4 to 6, okay, f prime should be negative. 4 to 6 should be negative. Therefore, this should be decreasing. Okay, I have also prepared a coordinate system where we will draw the graph of f using the information we have from the table of signs here. So we know that x equals 4 is an asymptote, a vertical asymptote for f. Also, y equals x minus 1 is an oblique asymptote for x, or for f. So when x is equal to 0, y is equal to negative 1. When y is equal to 0, x is equal to 1. So we have the following. We have the following oblique asymptote. Now, let us also note that we have a relative maximum at x equals 2 with function value negative 1. So when x is equal to 2, f is equal to negative 1. Also, we have a y-intercept at y equals negative 2. Okay, so let us now draw the curve f when x is in the interval negative infinity to positive 2. So from negative infinity to positive 2, it's increasing and it concaves downwards. It should look something like this. Then it reaches a relative maximum. Then from 2 to 4, it's decreasing and it concaves downwards still. So it should look like this. Okay, let us now note that at x equals 6, we have a relative maximum with value 7. Now, sorry, at x equals 6, you have a relative minimum, not a relative maximum, with value 7. Now, beyond 4, so from 4 to 6, your curve is decreasing and it concaves upwards. then it hits a relative minimum, then it's increasing and uh, it concaves upward. Oops. Okay. So our graph looks like this, and we're done. And I'll see you in the next video.